I'm going to talk today about a project that was funded by the RDA US and Adoption Project, where we took a science gateway, SEAGrid, and a science gateway is known by many things depending on where you are. This is a virtual research environment, a virtual platform, a science portal, or a science gateway. Regardless of what it's called, it's basically an abstraction of the computing complexities behind the scenes and giving the researcher either a web page interface or maybe a client interface to do their work with, and basically abstracts away all the complexities that are going on behind the scene. So this work was done by myself and Yu Lao and Guanchen Ran here at Indiana University. As Thomas said, if you have any questions about this, my email is here on the slide. I don't know how much time I'll have to answer questions here today during this adoption session, but please feel free to reach out and contact me if you have any questions about what I go through. In the demo or in the presentation here, I hope to talk about what SEAGrid is, talk about the RAPID. RAPID is a test bed that allows PID infrastructure to be accessed, or a digital object architecture, many call it, or fair digital objects. Then we'll talk about those two systems that are integrated together. We will do a brief introduction to the adoption project, talk about implementing FAIR from a technical perspective, or what FAIR means in the form of infrastructure and what can be done really before you begin your research to make the data products and in fact every step of the data more fair. We'll do a quick demo, and I hope to keep that very, very quick. And then we'll talk about PIDs during these computational workflows and get to my conclusion. So keep in mind that this scenario is for researchers who use a science gateway to do their research. They're concerned with digital objects they use and produce, and they want them to be fair. They want their work to be reproducible beyond the science gateway, so they want to be able to hand it to somebody who doesn't necessarily even know what science gateway they're using or what virtual research environment they're using or accessing, or may not have authorization to access that, but they still want the data to be reproducible. So something that's independent of the research environment that they're working in. And they want to share these steps, not just share the data at the end of the workflow, but share the steps on how to recreate or reproduce the calculations and analysis that are being done, and to share that easily with their collaborators or within a publication. And then they may want to reproduce a workflow with some tweaks, either running new data with it, updated data, maybe changing software versions, or some other way, tweaking the workflow that they've done previously to come up with new results. And they don't want to have to recreate the entire computational workflow from beginning. So this is really who is targeted with this work. And before we go on, I'm going to remind you of the FAIR principles. The FAIR principles are pretty important here. And this slide, Luis Benino from Leiden produced and pulled out really what's in green here in the FAIR principles as what we could potentially have a technical solution for. And the stuff that's in blue or black, depending on your screen, is more of the community instituted standards that really the technical framework allows but doesn't enforce. So just a reminder that bindable really is contingent on having globally unique identifiers, or PIDs, being able to describe data and metadata, or with metadata, and have that explicitly include some identifier to the data it describes. Accessible means that these are retrievable with a standard protocol, and that protocol is open and free, and allows authorization and authentication when necessary. What I show you today, authorization and authentication are not necessary, so we won't talk too much about that. And then the data type registry, which is again a RDA output, is used for this interoperable step where you have a accessible shared language for representing the knowledge. All the data that is captured is also typed in a data type registry. So you can actually have, machine actionable or human readable forms of what the data really means when you get a piece of metadata or data. So SEAGrid itself is the science and engineering application grid. This is a gateway that is built with Apache Ariavada and that middleware framework. And this adoption really, and what we've done is looked at small molecules and their fluorescent properties. This was the science use case behind this. With it being built on Apache Ariavada, we can then, if we can do this one single use case, we can plan to extend to the mini gateways. I think there are somewhere around 40 of them hosted at Indiana University at this point that use Apache Ariavada as the middleware framework. So this is then easily integrated, or at least able to be integrated with other science frameworks that may use this work. So the Rapid Testbed itself really came from work done within the Data Fabric Working Group of RDA. It's a cyber infrastructure for minting PIDs, resolving those PIDs. It includes a data type registry for describing the metadata, and then a protocol called the Digital Object Interface Protocol for doing operations based on those digital objects and the metadata that is captured there. So basically, this is a cyber infrastructure to implement the technical components of the FAIR principles, or some of the technical components of the FAIR principles. And it leverages several RDA outputs and recommendations. The PID Kernel Information Strawman Profile is a profile of metadata that is captured within the data type registry that basically defines some set of fields that are necessary to do for the protocol to do the operations. It has some base required metadata, profile fields that allow basically both the technical locations and the provenance information and such. And this was produced again by the PID Kernel Information Group. It uses a data type registry where all of the data is typed for both machine interoperability and then for readability and adjustment. And it really heavily heavily leverages the work done within the Data Fabric Working Group, where it was really conceived that putting together some of these outputs into a fabric of services was really the next step along the lines of creating a data fabric or a data cyber infrastructure. The RAPID was funded by the National Science Foundation in the US, and if you want to learn more about that project, the link is included here. So the RDA Adoption Project was really a 6-month project to see if we could take these small fluorescent molecules and integrate them with PID services that E-RPID allows, or RAPID, and provide some fair, so provide a version of a fair science gateway. Really, this workflow here, this generic workflow, it describes the steps from raw data through some preparations or data munging into intermediate data products. It's sent through some number of iterations to a final data analysis, and finally final products. This is again a very generic version of a workflow. They're much more complex than this in the end, but you can see along the bottom that we're assigning PIDs along every step. So the raw data, the intermediate data, and the output data, or the final data products all get PIDs, but along with that, the software used for the varying steps of the workflow, and really the workflow is defined within PIDs that can then be resolved, and you find metadata about the individual steps of the PID. And I'll show a simple example of what that looks like shortly. So, and I guess I'll show it now. the workflow PID looks something like this. So when you start a VRE run, it's assigned a workflow PID. This is split into 3 basic parts, and this is again a very simple workflow where you have input, you have some set of software, and you have output. Now, from the input, this splits into various different, both the data and the various different commands that are fed to the computing. In this case, the data consists of a molecular charge and then the coordinates of the individual elements within the molecule. You can see here that this looks like a tree. In the end, this probably workflows are much more complex than this, or real science workflows. So it would look much more like a directed acyclic graph than it would a tree, but this gives you a simple idea. And basically each of the steps along the way and each of the pieces of metadata involved with the run are assigned to PID, so you can potentially replace or, as I said earlier, tweak workflows with something like just a new software update or a new set of data, or you can compare the outputs to new runs, whatever it may be. These can be mixed and matched by knowing the PID. So looking at the time, I will do just a very quick demo here. Oops, before I go into conclusions. So what this looks like in real life, this is the SEAGrid homepage. It's available at rapid.seagrid.org. If you log in here, you're given a login prompt, and I'm going to use Gaussian 16, which does computational chemistry and does some molecular modeling. You pick an application. In this case, it brings up what is the start of your workflow. You can see here it gives it a timestamp. It's putting it in my default project. I'm going to add a file here, and this is neopentanediol, which I okay. So that uploads this basic molecule. The great thing about this is as soon as you start your workflow, so you hit this save and launch button, it does the calculations, but it immediately gives you a workflow PID that is resolvable externally. So you get this PID, you can go to handle.net and get some information about it immediately. So if I put that in here, I had a copy and paste error. Now I went back too far. So let's see. Maybe I didn't paste it all. So that's the problem with doing live demos, right? Is you run into potential problems. So I will see if I can pull up a older one that I've done previously. And you can see here, this is the Gaussian output data for a previous run. It's recorded immediately. You can find more information about it. This gives a creation date when it was done. If I dig a little bit deeper, I can find out the URL of the data product. So following this login, you can get to the end data product. So I'll go back to my presentation because my demo went midway south. The important thing there is that as soon as you hit save and run, as this is before it's even queued, you get a PID that is then persistent and described external to the gateway. So let me put my slides back up here again and go with the conclusions. So SEAGrid has been integrated with the Rapid Testbed services to implement fair science workflows. We're currently exercising this with the remainder of the adoption time, which is basically until the end of the month. We're going to run as many of these fluorescent molecules through the system and see if we have any issues with this. We're hoping to get tens, if not a few hundred, of these fluorescent molecules run through the system. These are all assigned workflow PIDs, which basically record the entire computational process used, including the software, the input, the output, and any parameters fed to the computing. And with the PID, you could basically recreate the entire computational workflow externally, knowing nothing about the virtual research environment or science gateway. Though you probably wouldn't want to recreate it. A more realistic scenario would be, as I mentioned, you want to run some new data through it. You want to replace your run with a newly released software version. You want to feed some different parameters into the workflow to see if you have if they match the results. And there's no access necessary for SEAGrid or the gateway to have the information you need to recreate a workflow. And as you saw from my FAIR slide, this directly inputs the findable, accessible, and interoperable principles, not as much the R, but it really builds that foundation that you can get to a FAIR data, or I'm sorry, a FAIR science gateway. In both the metadata is extendable, and this is extensible to other science gateways based on area of ADA, but we're hoping to produce best practices for other gateway type softwares or middle frameworks, so people can use a piece of software that allows them to reach out and basically stamp these PIDs on various items within their workflow. We'll produce both a piece of client software that allows interaction with a handle service and DTR, and then some best practices along with that. And as I've said several times, but I'll reiterate here because it's the reason I'm talking today, that this project leverages several outputs made available by the RDA community. And in fact, these FAIR science gateways in themselves could not exist as we've done in this project without the RDA community. So I'll wrap up there, and don't know if I have time for questions or if I ran long there, Daniel.
Yeah. Thank you very much, Rob.